Hi, in this video I will talk about Newton-Cotes quadratures. Let me start with closed Newton-Cotes rules. As we mentioned, for Newton-Cotes we can have arbitrary points. Here we choose n plus 1 points. And to start we need to compute the weights W and the error E. And the weights are computed by the integration from a to b of Lagrange polynomials, and the error is the integration between a and b of the Lagrange remainder. Okay, so for simplicity we use equi-space points, and using these points the rules are tabulated. So basically the position of the nodes can be written in this general form. So this is the addition of the first point by some number of intervals. So the interval h here is the distance between b and a divided by n, and basically h is graphically represented here. Okay, so the equi-space interval. So since the first node is a, basically we can substitute x0 by a, and then the rest is the same. So this I, basically the index of I can change from 0 to n, and it can basically identify the nodes in the interval. Following from the previous expression, we can change the variable of x by the addition of x0 to alpha h, where alpha here can be any value. To get our integration points from this change of variable, basically we can assign alpha to discrete values of 0 to n, and basically we can obtain our integration points. So by changing this variable, basically the Lagrange polynomial and remainder can be written in this compact form. Okay, so basically this change of variable basically leads to this compact form for Lagrange polynomial, and also this compact form for the Lagrange remainder. So both of them are written based on alpha, and also here in the remainder we have the h, the equi-space interval h. Here we write again the quadrature or numerical integration formula, and for the weights, the integration weights, again we write the formula for the weights, which is the integral from a to b of the Lagrange polynomial. And this Lagrange polynomial, basically we obtained it in the previous slide as this term, you remember. And for dx, basically since x is equals to x0 plus alpha h, you remember the change of variable, therefore the dx equals to h d alpha. So basically the h comes here, we can take it out of the integration because it is constant, and this is the d alpha. So the error can be obtained the same way. So the final formula for the error, basically you can see here. Okay, and this term, this product, again you remember that we mentioned in the previous slide. The first Newton-Cotes rule is the trapezoidal rule, where we consider n equals to 1, or in other words, when we have 2 points. So when we have 2 points, then the polynomial approximation basically is the degree 1 or a line, and based on this then we can obtain our weights and error. So since we have 2 points in the trapezoidal rule of n equals to 1, basically we have to compute 2 weights associated to the 2 nodes. Okay, and then using the formula for the weights, basically we come up with h divided by 2 for both weights. Okay, So basically W0 equals to W1 equals to h over 2. So for the error term, again, we can use the formula that we introduced in the previous slides, and then we can come up with this term. And for converting this integral to this, basically we use the mean value theorem for integration. Okay, so having these three terms, basically we can put it in the quadrature formula. Basically here, this is the sum term, W0 fx0 plus W1 fx1. And since W0 and W1 is the same, h over 2, basically we have this term, the first one, and the error term also, you can see it here. Another rule of Newton-Cotes is Simpson's rule, where n is equal to 2, or basically where we have 3 points. Okay, so in this case we have a quadratic polynomial or polynomial of degree 2 for the approximation of the f function. So since we have 3 points for the Simpson's rule, basically we have to compute the 3 weights associated with these points. Okay, W0, W1 and W2. Again, putting the terms in the integral for the weights. Basically we come up with these weights for the W0, W1 and W2. So we can do the same for error. So putting the terms in the integral formula of the error, and then we can come up with this term. So I know that here n is equal to 2, but the order of the quadrature becomes 3, which is higher than expected. So you remember that the error term, we can write it as this form: c f basically q plus 1 order of derivative for f, and then basically we call q here the order of quadrature. So since here this is 4 basically for the Simpson's rule, so this is 3 plus 1, and then the order of the quadrature is 3. In general, the error for closed Newton-Cotes quadratures depends on the choice of n. Okay, so if n is odd, the order is the same, n. So you see here that the order of derivative for n is n plus 1, and the order of the quadrature is n. But if n is even, then the order is 1 more, so it is n plus 1. So here you see that the order of derivative for f is n plus 2, which is n plus 1 plus 1, and then the order becomes n plus 1. So it means that if n is even, then we can exactly integrate a polynomial of degree n plus 1, or 1 more than the choice of n. Okay, this is a summary of the closed Newton-Cotes formulas for different choice of n. So for n is equal to 1 is trapezoidal, 2 Simpson, and 3 is the second Simpson. So you see that with increasing the number of n, also the terms in the sum also increases. Okay, and I note here that the order of quadrature for Simpson, in the case of Simpson, is the same as in the case of second Simpson. Why? As I mentioned before, when we have an even number for n, for example here is 2, n is equal to 2, then the order of quadrature is 1 more. So in the case of Simpson we have 3, 2 plus 1, and in the case of second Simpson, since it is odd, we have the same. So in the case of second Simpson also is 3, so it is the same for the Simpson and second Simpson. For open Newton-Cotes quadratures, when we want to calculate the integrals over the open interval of a and b, not the closed one, basically we can follow the same idea that I presented before, but here we have to choose the first point for the integration 1 step more than a, and the last point 1 step less than b. So here in this graph, we want to integrate between a and b, this function. And basically, for choosing the integration points, we have to go inside the interval. And then the first point basically is one step h more than a, and the last point one step less than b. Okay, so here and for the rest of the points, basically we do the same, the equal space points that I presented before. This is a summary of quadrature formula for open Newton Cotes quadratures. So I note here that for the open quadratures, we can also just introduce one point and calculate the integration, while in the closed quadratures, the minimum points that we can choose is 2. Okay, so you see the expansion of the terms based on the choice of n, and also the error. So here also the order of the quadrature, basically you can see in the error term, so it is the order 1 and 1 here, and 3 and 3 here. So you see that for n0 and 1 we have the same quadrature order, and for n2 and 3 also we have the same.